Hi, Professor Lee here. In this lecture, we're going to go over briefly software engineering. And I'm doing this in two parts. So this is part one. So what is software engineering? Software engineering is a discipline in software development or computer science, and that discusses systematic and cost-effective techniques for software development. These techniques help develop software using an engineering approach. What's engineering approach, as we are pretty much well aware, it's basically the application of scientific principles to build things. Now, some examples of engineering include mechanical engineering, electrical engineering, civil engineering, aerospace engineering, etc. Why is software engineering relevant? Good question. So from the perspective of business or a software company, software engineering can be a competitive advantage. It is the difference between very cost-effective project management for software development versus some project that takes a lot of time and money and may not even deliver. And this is essentially important to a software development company where the principal activity is developing software. So it's almost a must done well. Now, from a student's perspective, through this, there are a couple of skills that you're going to develop. One is to develop you're going to develop a skill to develop large software with a team. Now, for a small software, a project that you do it on your own, a little bit, coding and testing, that's fine. But when it comes to a company developing software, a team is mandatory. And to develop many of the software that you use daily, on your phone or on the web, most of the time it's done by a team. So the team needs software engineering principles, techniques to develop that software. And the software can be very complex. So you'll be introduced to the techniques that are going to help you deal with that complexity. And also, the software engineering includes the techniques for managing a project or leading a software development team. So those are some of the skills that you can get started and then you develop over time. And this by itself can be a course. And so we're now just having a week and we're going to just basically go over this in a very brief manner so that you're familiar with the concepts. First thing that you would like to know would be software development lifecycle, or SDLC. And this is something that would be discussed in most software companies. They may have a variance, basically their own software engineering practices. In one of the extra activities for this week, you will take a look at a real life example how software engineering is done. But for right now, let's go over some of the theoretical stuff. Software has a life cycle. It does not, necessarily run forever. Sometimes software may have to be deprecated and then removed completely. And this happens a lot in a company. And so the life cycle of software is just describing the different stages over which a lot of software evolves from the initial conception to delivery to the customer, and then eventually may be discarded. Now, the development is one of those phases in the life cycle. Now, specifically for that development activity, there is also a life cycle for development. Now, this is kind of the focus here for when we talk about the SDLC models. So the SDLC describes different phases through which a software evolves. That is comes with activities described during each phase. Over here, you see the waterfall model. And the waterfall model is a classical model that usually we start with describing the software development lifecycle. Now, this phase is here, it's sequential. First phase, feasibility study. Feasibility study, in this phase, the team develops an overall understanding of the problem, perhaps talk with the customers, figure out what is their problem, and then we come up with the strategies, and then you evaluate different strategies, the pros and cons analysis, and then pick a strategy to go. And the outcome of the feasibility study may be this project will not go forward. So it's a go, no-go decision as well. And then once that is done, say, suppose we're going to do it, and then we analyze the requirements and then produce a document called SRS. It's the software requirements specification document. Now this SRS is, somewhat formal, and this is the basis for further activities from now on. And then the next phase is design. And the design phase is basically to turn that SRS document into a technical design document so that the engineers can start working on coding and testing. And that technical design document usually includes the architecture of the software. And then you'll be introduced to architecture in part 2. And then the team go ahead and code it and then test it. There's different kinds of testing, which will be introduced later on in part 2 as well. And then the really majority of the software life cycle is about maintenance. In maintenance phase, the bugs may be fixed, the performance may be improved, maybe there's some minor changes that will be introduced. And then sometimes we need to move the software from one server to another, or from one platform to another platform, different infrastructure, maybe going to cloud. And so those changes, when they happen, then there will need to be changes made to the software as well. Perhaps we just want to upgrade the platform software that it depends on, so that there might be changes involved as well. So that's mostly the maintenance, and then we need to monitor the software, and then tune it over time. Those are the activities that can happen in maintenance. And then there are many models, SDLC models, by the way, and we're gonna just introduce a few main things here. And then so the waterfall model was improved upon by some folks that come up with this RAD model. It's called a Rapid Application Development Model, because one of the main thing with waterfall model really is that there is not enough feedback loop. What you produce may not be what the customer wants, and also there is a very inefficient process to accommodate changes. So the RAD model comes up to say, well, let's actually get the customer and developer talking. So as you see the circular arrows here in the user design construction phases, you may draw the parallels with the waterfall model is just condensed a little bit. And here, this is more of interactive between developer and customer to figure out what the customer wants by rapid prototyping, essentially quick and dirty prototyping. Once you figure out something that customer wants, and then the prototype will be enhanced to produce the actual software. Now, this process is gonna be, well, obviously, it will be faster, and then also produce something that most likely customers will want. However, the drawback of this is that it may lead to poor design because through that quick and dirty way of doing things, and then you improve upon that design, that prototype, it may not lead to a good design, and the quality may suffer. And also, this way of working, it can be very infeasible if it's a complex, large software. So this probably works for small and medium size, but not necessarily for something that's pretty large. Additionally, because the intense involvement of this interaction between the customer and developer, more scarce resources have to be committed to this project. So there's pros and cons with this model. And the next model that I'd like to introduce you to would be called Scrum. Scrum model is one of the so-called agile models. You probably have heard of agile methodology, agile process. There's a number of those models. For example, extreme programming, lean development, and then you have Scrum. Scrum is perhaps one of the most popular models nowadays because it's proven to work pretty well. And the agile models were designed essentially to accommodate change requests quickly because we realize by the time the software comes out, the customers change, the requirements may have already changed because the market has changed. So we have to be able to move quickly. If there's something that we want to do, we gotta get this out fast. And then once they've seen the actual software, they may change their mind as well. So instead of planning for a month or even a year ahead, we say, well, we don't know that far ahead. Things gonna change. And so that's only plan for a few weeks that we can see. So this is the methodology essentially is the hallmark of agile model is iterative development in a short time box, and then usually done by small teams. There is a list of principles called Agile Manifesto that you may go to and check out. It's very short, and I'm not going to repeat here. You can read more at agilemanifesto.org. The link is also in the slides in the notes. Now, back to the Scrum specifically. This diagram shows some of the essential elements of this model. And the software planning, essentially there's an evolving document called a product backlog that contains all the things that we want to do. Mostly the product backlog contains, functional requirements and non-functional requirements, or essentially everything you want to do with this particular product. And they are continuously, refined, prioritized. So each sprint, which is a time box of 2 to 4 weeks, the team will pick the top few stories that it consider can deliver based on its resources and time. They will commit to say, we're going to deliver these 5 stories. It's called stories because the items in the backlog, they are written in the user's perspective. And that's similar to the requirements documentation, SRS. But in a much lean, short fashion, not as formal as verbose. But anyways, so the team will pick a couple of stories and then start working on them in the sprint. And sprint is a defined time box of 2 to 4 weeks, whatever the team decides to be the right length. So there will be a sprint planning where those user-oriented stories get converted into technical stories. The technical stories or technical issues, they are much closer to the engineer's language. And it has, it may refer to some kind of architecture or some, design doc. The designs may be part of the story, say these are the things that we're going to do in the beginning of the sprint. So anyway, the team decides on what to do and plan them and then get them clarified to just enough understanding so they can get started. And those things basically put it into this thing called, another backlog that's only for this sprint. Is much smaller, very focused, only for this couple of weeks. And then the team, it's called a Scrum team. There are different roles. We'll get to this in a little bit later. And they will hold daily meetings called daily Scrum meetings, or sometimes called stand-up meetings, because the team members, if they're physically together, they would be standing up so that the meetings will be very short. The recommended length is no more than 15 minutes. So it's very short. Essentially, you answer 3 questions. What did you do yesterday? What are you gonna do today? Did you have any roadblocks? And so that the other members of the team can help you remove, so that you can move forward. Once that is done, there will be a review meeting in the end to look at the things that are done, kind of like acceptance or validation of the things that are delivered, that are working. So usually the product owner who owns the product backlog that manages the customer requests, the requirements, they will attend this meeting to look at what's been done, and this is what they had in mind. And once they are, accepted, essentially validated, and then the product will be shipped. And this may be just an increment of what the existing product. Every shipment is kind of small. It's not a big bang delivery. So that's kind of it's called the incremental iterative development. And then at the very end, there will be a retrospective meeting to figure out, to reflect on the sprint. What did we do well? What did we not do well? What are we going to do now to improve our process? It's a continuous improvement portion of it. So this is how Scrum works. Pretty simple. Now, we've got our methodology, the model, and we have a team that's set up to go. Now we need to manage the project. Now, the management of the project, there are many different tools. Here, I'll just introduce a few common tools that are used. The first one is called the PERT chart. PERT, it stands for Program Evaluation and Review Technique. This is a tool that's used in project management in general, not just for software projects. And it helps with the planning. When it comes to planning of a project, a couple of essential questions you'll have to ask. What is to be delivered? How long does it take? How many people and other resources are needed? Basically, how do we allocate resources to the project? Well, the first question, what is to be delivered? That is the very beginning portion of the SDLC model to analyze what the customers want, and then break that down into some kind of document that, or SRS, tells the team what needs to be done. But then the key question after that is, okay, now we understand what needs to be done. We need to figure out how long does it take to finish it. That's a very tough question. Depending on the SDLC model, there's different ways to do that. So here, just to show a PERT chart, it's just one way of approaching this. for each activity here, you have 3 numbers. Those are the estimates of the time. So here it says, well, for writing the specification, it takes in the worst case, it takes 20 days. In the best case, 12 days. In most likely case, 15 days. So it's like best case scenario, most likely scenario, and best case scenario, or worst case scenario. That, these numbers are put into that box for that activity. So once you're done with the specification, this is just an example of some software that has a, front-end GUI part and then database backend, just to show the concept. For example, the database design, may take between 40 and 60 days. And then the GUI part is, also designed and coded. And then these 2 parts will integrate and test it. And then in parallel, maybe a user manual is written. So this is just one way of seeing, you estimate each individual activity, the essential activities, and they put them together in a chart. It's called a PERT chart, and it helps project planning. And then once you get this done, you have a different view of looking at this, putting them into the specific timeline. This is called Gantt chart. It's actually a specialized bar charts. You see this in the regular bar chart, X and Y are reversed. So this is another popular tool. And the box where it has a shaded and unshaded part. The unshaded part is just the slack, essentially showing the worst case how long it's going to take. So you can put this in a Gantt chart. And that's just another way of planning. Now, this is really useful for knowing when a certain activity is going to start and when it's going to finish. And then so you may allocate resources accordingly. Now we got the general planning done, but then a big part of it is to staff the project. So in what format are we gonna put the people onto the project? So there's different ways of organizing the team. Suppose it's a complex software and needs multiple teams. So one way to organize this is that you have multiple project teams under a management team. And then you may go by functional teams where members of the teams actually come from different functional groups. You have a design team, engineering or coding team or testing team, project management team. And then you have various different members allocated to various different projects. Essentially, some of them are like a shared resources. So it's just organized by their functions. Now, when we look at a specific team, so how do we actually organize a single team? So there are 2 popular formats here. On the left, you see a hierarchical team where you got a project manager that manages the senior engineers, and the senior engineers manage the junior engineers. Perhaps you have each senior engineer managing one small team. I don't know, one small portion of the team. But this hierarchical structure, in some organizations, the senior engineers may not be at this level, may just be at the bottom level. But this is kind of a common normal structure here. And then for the companies that actually adopt Scrum, you have 3 different roles in that team. And it is more of a flat structure and more democratic. You have Scrum Master that actually enforces the Scrum process, make sure those essential activities happen. And then you have a product owner that owns the product backlog and manages what the customer wants, and then validates the software at the end of the sprints. And then you have a development team that consists of engineers, domain experts that actually develop, the code and deliver the software. You may also have somebody that's called a DevOps. DevOps, it's short for development and operations. And there are those folks that are helping the team to get the software running on the cloud, for example, or onto different servers, get those things. So there are those portions of the various different things that different people you may have in the team. But primarily you have three kinds of roles here. And the other activities is just kind of just different way of looking at the same chart that you see before, the diagram where the Scrum model. This is the team structure. So now we got the team, and then what comes after that. Now essentially we just want to understand how to design the actual software. So how do we design the software? There are many good design principles, and one of the tools that embody some of those principles is called a unified modeling language, which is it's a standard that's used widely in the industry. The UML diagrams, there are many, and some of them are used more often than others. For example, a class diagram shows the different classes you may design for a particular problem, and then how they interact with each other, how they comprise the software. And actually, if you look at this particular diagram, this is just like a class diagram, in fact. And you have a superclass diagram here, and then you have subclasses. So essentially two types of diagrams for UML. Behavioral behavior diagrams describe the behavior of the system. And then you have a structural diagram that describes the structure of the system, the software. And in the structure category, you may also use the component diagram to describe the various components of the software. You may have a front end, you have a back end, you have the back end, you may have a middleware, you have a database, that kind of structure that you may show in that diagram. It's a communication tool. And then you may also use deployment diagram to show that the software is running in multiple data centers, multiple data regions, and then how do they interact with each other. If one data center goes down, how does it fail over to another one? This could be described in a deployment diagram to show that concept. And then the behavioral diagrams, some of them are, for example, the use case diagram is a diagram that describes the actual user functionality from a very high level, what the user can do. What are the use cases of this software from a user's perspective? And then you may use a sequence diagram to show the specific action of a single request from the user to perform something. Let's say the user wants to log in to your software, and that login request goes to, is illustrated in the sequence diagram, and which will show various different components of your software, how they are handling this one request and then responding to the user request. So just as an example, some of those diagrams, we're going to get into them in more details throughout this course. And then designing the software nowadays is, well, there's different design methodologies, but object-oriented design is perhaps the dominant form of design nowadays. It has been proven to be superior to the earlier design methodologies. So, here it's just a basic example. It doesn't mean that every software is designed this way, but this just shows you what could happen if you design something with object-oriented design or OOD. So when you start designing, you may, design a user interface or some kind of basic prototype of the interface. You may also come up with the SRS document or some form of a requirements document that's and then you put this information together to design use a use case diagram from UML to come up to illustrate the main use cases of the software. And then you want to get into more detail, turn that into a technical requirement. You design a domain model, essentially the classes or the objects. What are the main objects you have in the system that going to interact and deliver that functionality? And this domain model will be further clarified with a class diagram to show the structure of your program. What are the main classes that's gonna you're actually designing? There are components that will handle the requests from the user, and then how do they interact with each other? Then you start coding. So the essential is it is going to show you just a couple of elements from UML that you may use to design, and we'll get to some exercise later on so that it becomes more concrete. Now, next thing that I would like to just introduce you a little bit, and we're going to have a little more discussion about this, is the ADT, or abstract data types. The abstract data type is a data type that separates the logical properties from implementation details. And there are some of the related concepts about ADT. First thing is data abstraction. The data is abstracted. Essentially, the way for the outside world to interact with your ADT is through its public interface. In the case of a C++ class, which is actually embodiment of ADT, that would be its public functions of that class. And then the data structure. Now, what's the data structure? Data structure is, think about in civil engineering, right? So an architect that builds a skyscraper. The skyscraper is made of the basic materials, concrete, steel, and bricks or glass or whatever. In the case of a programming language, you got the built-in data types. You have integers, floats, or you have some of the just those basic data types. There's elements, and then you put them together into a higher level structure that will provide some kind of meaningful function, like for example, linked list, which will look into that in much more details. And that provides a very useful way of organizing your data that has certain properties that's very useful for solving certain kind of problems. And then just like any other data type, abstract data types has a name, it has a domain, basically the set of values for this type, and then the operations that you can perform on this type. So that's ADT. Now, why is ADT good, and why do we want to learn about ADT? It offers encapsulation, which is a good design. Encapsulation allows you to evolve your ADT over time without breaking your software. You can still keep your interface intact while evolving your internal structure because your data is encapsulated. And then it offers high cohesion. The high cohesion means that the related elements, they stay together. They are part of this ADT. And then because it has a high cohesion, it also offers low coupling because unrelated elements are in separate ADTs. And then these ADTs they interact with each other. They don't have to be tightly coupled. So it's called a loose coupling. Loose coupling is a very good design principle when you design a software that you want to make sure that you can evolve each component independently. You don't want to touch one thing and then 100 things break. So that would be fragile. So this ADT will essentially what the things that we're going to learn for the most of this course are much about the ADT, and then we're going to learn a lot of them. And so yeah, this is it for the first part of software engineering. Thank you.